Next, we're going to learn probably the hardest thing that we're going to do this year, which is called Biot-Savart. We're going to start it today. We're going to continue on several times until we get this. Okay? We're going to use this right here and a couple of visual aids in order for us to actually see what's going on a little bit easier. Now, the first thing that we want to do is we're going to use what's known as a current element. Let me show you the actual Biot-Savart equation, and it's a little bit intimidating, but we're gonna pull it apart and make it a little easier. This is Biot-Savart, and the word Biot-Savart is that's a person's name. Might be two people, and I'm sure someone online would troll me for that. But yeah, you're smarter than me. You need to prove it. Go right ahead. Okay, there's a lot of stuff to define in there. First of all, you should know what mu naught is. We've already used that for the magnetic field due to a wire. 4 pi, obvious. I is the current in the wire. It could be a wire or a wire loop. In our case, we're going to use a wire loop. But what about this dl, r hat, and r squared? Okay. If I take a point in space, just any point, and this is my origin, and I'm saying I'm going to go from here to another point. Let's call that point 1, and we'll call this point 2. Let's say that this is the current coming out of the page, right? Well, this would be R, let's call it R1, and this would be R2. R is defined as the distance from a point to another point. We use R because it's a straight line distance and it's positive in all directions. I hat, j hat, x, y, z can be positive, negative, etc., and they're only in one dimension. R hat goes from here outwards in all directions. R can never be negative. And that's why we use R for electric fields, electric forces, gravity, etc. Okay? Now, as we move up the ladder and we're using I, j, k, and so forth, you need I hat to say it's a vector in the horizontal direction. J hat says it's a vector in the vertical, it's pointing in the vertical direction, and k hat says it's pointing, in the out of the page direction, I guess. Well, if we want to make these vectors, it's a vector if it has a hat, I hat, R hat, etc. And this one's going to be R hat. R hat, as all unit vectors, has a unit of 1. It just says outward is positive. Okay? So that right there is just for direction. This is the distance from some place to another place in a straight line distance. And that dl, that's a funny thing. So let's define dl now. What is I, scalar or vector? It's a scalar. Scalars do not have direction by definition, right? And yet for all of magnetism, we do in the thing we'd be going like, oh, that's the magnetic field. That's the direction of I. I is traveling that direction. But to be specific, when we're doing big equations, we can't call that a direction because it's a scalar. It would be like saying mass is going that direction. You wouldn't say the mass has a direction. You would say its velocity has a direction. Well, we have to change this to where now we have something pointing in a direction, and that's dl. This thing, I dl, is defined as a current element. Now, remember how an element is a piece of something. Like you have the basic elements that make up all of nature. A current element is a piece of a wire that has current in it. So if I were to take this to be my wire, and it has current flowing through it this direction. So here's I going this direction. We would call this little point on the wire, dl points that way. Right now, dl points that direction. dl points that direction. dl points in the direction of the flow of the current along the wire. That's all it says. And as we should already remember, that dl is an infinitesimally small delta L. And when we add up that was wrong. When we add up all of the delta L's, we get L. When we sum up all the little dl's, we get L. Now, if it's just dl, that's easy. If there's other things, we have to do antiderivatives, right? Okay, so do we all understand basic notation now? we have a small magnetic element, meaning we have a bit of the magnetic field created by a small piece of the wire. And when you add up all the little dBs, all the little magnetic fields, you get the entire magnetic field. Kind of follow me a little bit? Okay. Now, the problem that we're going to do next with Biot-Savart, and I'm going to do it, I guess I'll mimic this. The book actually tilts it so that it's going in the X direction. I'm going to do it in the Y direction just because that's what we have here. So the picture looks like this. We have a loop of radius R, and let's say that the current is flowing this direction. So the current is counterclockwise from above. You understand what I'm doing there? So the current is flowing counterclockwise as viewed from above. So at this point right here, I is going in, and at this point, I is coming out of the page. We all in agreement? If you wrap your fingers around it, shouldn't the magnetic field go up? Mm-hmm. We're going to take a point out here. We're going to take a point P. We're going to say this distance is Y. This distance again is R. And then we're going to make, this will be R. And this will be R hat, which points in the direction of R. Okay, and I guess I should probably do that. I don't know. So let's take this as our angle, theta. Now, if we look at the formula, before we actually did something where we said, you know, the acceleration equals my final velocity minus my initial velocity over time, and since time is a scalar, what this says in words, ignore the scalar because it has no direction. The direction of the acceleration equals the direction of the final velocity minus the direction of the initial velocity. If this, so, like when you're going around a circle, that's a terrible looking circle. Do that better. So if we have a circle and we say that this is my initial velocity and this is my final velocity, well, my final minus my initial gives me the direction of the acceleration, which is to the center of the circle. Well, let's look over here and let's read the formula for direction. It says the direction, do you see how those are all scalars? So this says the direction of dB equals the direction of dl cross the direction of r hat. Can you see it now? That's what it says. This direction equals that direction cross that direction. Here's I is going into the page, or dl is going into the page. Are we all in agreement with that? At this point, I is going into the page, dl is going into the page, IDL, the current element, right? Do you see how r hat is going this direction? Point your fingers in the direction of dl, sweep them towards r hat, and your thumb points towards dB, which is perpendicular to both of them. Which means that at this point P, that's the direction of the current element for this, or sorry, this is the direction of the magnetic field due to that small piece of the wire. You see it? I cross R gives me B. Now, would you agree on this side? It's coming out of the page, and won't it have a R here as well? Only now it's out of the page. Cross R gives me the mirror image, doesn't it? So this one's going to go this direction. If we call this, this will be dB right, and this will be dB left. And what do you notice about those?
Perpendicular.
You should see that they're not perpendicular. They're perpendicular to here, okay? It turns out though that the dBx, dBy, dBy, and dBx And what do you notice about them?
X's canceled.
The x's cancels
The Y's out.
and the y's add. It looks a little bit like this. Here's our current in this direction. So we wrap our fingers around and we expect the magnetic field to go up. Let's take this as our point. For this side, we have R going this direction, in any direction, right? But when it crosses here, current, R, magnetic field, that direction. And hopefully one of these magnets will be strong enough to help me out here. And from this side, R, our magnetic field will go that direction. And this too, I want to lay it back here. You should be able to see. That probably won't stick, they're aluminum. So, at this point, we can see that the x directions cancel and the y directions add. Do we see it? So now let's just try to imagine a little bit. What if I took these and I brought them down? Again, I don't have time to move these, but you get the idea, right? So imagine that these are moving down here, and you can see that as I move them down, you see that when I got to the center of this, when I got down to here, they'd both be pointing up, wouldn't they? And the x's wouldn't cancel at all, the y's would be 100%, and that's why the maximum magnetic field is in the center of the loop. And when I keep them going up and up and up and up and farther away and farther away and farther, imagine they're going up to the ceiling. You see how the x's are canceling? And that's why far from the loop, there's no magnetic field, because they cancel and don't add anymore. And if you were to take these two current elements, or these two magnetic fields going this way, and we were to sweep them up all the way around the loop, okay, we understand that they would cancel in any one position would cancel with the same one on the other side, wouldn't it? So if we add up all of the little dBs, all the dx's would cancel and all the dy's would add. So what would that look like? So I'm going to show you some notation. Now it is possible to define r hat as ijk. It is possible to do ijk and do this explicitly. I'm not going to do that today. It adds a level of complexity that's irrelevant. Not irrelevant, but harder than we need to do. So I want to show you some notation. Would we agree that before we've done stuff where we've said, this is vector 1, this is vector 2, and that's vector 3. In other words, vector 1 plus vector 2 equals vector 3. We all in agreement we've done that, okay? Well, let's do the same thing, but instead of vector 1, vector 2, would you agree that? Would you agree with that?
Yep.
If you add up the x value of the x component and the y component as vectors, you get the entire vector. Well, if we use a little bit of notation here, and I add them up, okay, that's just a summation. Well, but what did we learn over here? What is the summation of all the little dx's, of the dbx's? They are? So we have just given you an explicit way to say those cancel and these add. So now we've got to figure out what this equals. So what we have just done up here, we have just figured out that this equals dB in the y direction, which means we're going to have a sine or a cosine, aren't we? So we got to figure out, is it sine or is it cosine? And the unfortunate, this is the most difficult part of the whole thing. We have to figure out where the angle is. So let's do this. We're going to look at two angles. We have this as a possible angle. We'll call that angle 1, and we'll call that angle 2. Well, that's really hard to see. So we have angle 1 and angle 2, yes? I want you to see, you see my thumb is pointing in the direction of dB, and this is my hand along R. As I close down like this, which angle is also closing? Angle 1 or angle 2?
Angle 1.
2.
Uno.
This and this are attached. So
Oh, dB is attached.
if I take it like this,
Someone.
you see how these two are both closing down.
Yeah.
Therefore, those are my angles, and that's one of the biggest mistakes on Biot-Savart, is figuring out which angle is which. All right, so now, if this is theta, then dBx equals
0.
sine or cosine?
Cosine.
Cosine. That means this equals sine theta, and now we can get into business. So now, when we add up all the dBs, we're actually gonna get the net magnetic field. Let's take out all the scalars. It's gonna be mu naught I over 4 pi. Isn't R constant all the way around? R isn't changing, is it? So that's a constant. And we're gonna have our adding up here, but remember that cross product? We found that it's gonna be DL, and then we need to make it into the Y component, which is the sine of theta. That's all this says right here, is do the trig and figure out what's right. Is that a constant or a variable? That's a constant. Isn't theta constant?
Yeah.
I'm gonna pull that out too. And now I get the magnetic field equals mu naught I sine theta over 4 pi r squared. That's not that difficult so far, is it? We good so far?
That's an angle.
Right? Well, you know, we could define sine of theta with what we're given here. And sine theta, from what we're given here, would be opposite over hypotenuse. Remember how we did that in that earlier problem where we had the 2 points? So it's going to be big R over R. We good so far? And let's go ahead and stick that in. So now we get B equals mu naught I big R. That's going to go into the bottom, which is going to give us 4 pi r cubed. But you know what? We can define R as well. Because isn't R the hypotenuse? Which equals square root of y squared plus r squared square root. We remember that earlier too, don't we?
Yeah.
Remember I told you that was a pretty important problem. It would be,
Yeah.
keep coming back, wouldn't it? Glad we did that a few times. Sorry, this is supposed to be there. All right, let's plug her in. Can you still see?
Si, senor.
Okay, you can see, senor. Okay, so we get mu naught I R. I forgot the DL, didn't I?
Yeah.
Yeah, we're gonna do that in a second, so let's make sure we put that in there. DL. Okay, so now we get mu naught I R over 4 pi y squared plus r squared to the 3/2. We gotta deal with this DL thing now. And what is the summation of all the DLs? Just L around the entire loop. And what is the distance around the entire loop?
Circumference.
Which is just 2 pi big R.
Oh.
And this is just the circumference. Adding up all the little DLs all the way around, and that gives us our grand finale, where the magnetic field due to a loop of wire equals mu naught over 4 pi I R 2 pi r squared.
No, it's not square.
No, 2 pi r, that thing is it's gonna be squared here in a second, over y squared plus r squared to the 3/2 in this case, it will be the j hat direction or vertical. And obviously, we could combine the r's into an r squared. Now, the hardest part, I think, is getting this figured out. And figuring out theta and make sure you sign the theta in. This is the hardest equation we use all year. And it has shown up on the AP test once in a while. Okay? But notice a lot of it's just understanding notation, isn't it? It's not absolutely horrible now that we've known other things, right? But you just have to keep all track of it. Now, if we wanted to, let's go ahead and combine all this stuff. We'll keep that as this, hopefully this pen will work well. Can you see that all right, Louis? Or not enough? Was the black better or was that good?
It's
The red's better.
Yeah.
Okay, well, let's do this. What if we take this and we move it down to the center, right? And we put this point right there. What does y equal?
0.
0, right? Because we bring it down, y gets smaller, 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 smaller. All right, so this equals 0. So then it would be b, all right, equals, now why did I add that? Because I have that there, which says it's a vector, okay, because it gives it direction. Mu naught over 4 pi I to 2 pi r squared over r squared to the 3 halves. Do we agree with that? And we still have the j hat. Well, what does this become? Just r cubed. And r squared over r cubed is just r. So now we have, oh, and you see how these cancel? That's gonna cancel, and that's just gonna give me 2. So it's gonna be mu naught I over 2r. Now this sure looks an awful lot like that equation over there, doesn't it? Because we have an equation that says this: B for a wire equals mu naught I over 2 pi r. Do we agree with that?
Yeah.
There's a pi missing, and I love pi, so this bothers me. Okay. Why are they different? This is due to a straight wire a distance r away. This is a loop of wire, and you find the magnetic field at the center of the loop. These are not the same. They look very similar, but they are not. The other thing, obviously, we could do with this equation, I guess we got mu naught equals, so it's mu naught I over 2r, is we could make y really, 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 really big, couldn't we? And if y gets to infinity, then this equation would become, and we have all this junk on the top, mu naught I 2 pi r squared over 4 pi. That becomes big, that becomes irrelevant, and it just becomes y cubed j hat. And that's the basic question: why far away from the loop does it decrease as a 1 over y cubed versus y squared? Because as you're getting farther and farther away, the x values are canceling more and more and more quickly, and it's decreasing to 0 very rapidly.